On that, I would like to welcome our first speaker, Leemann. Lucas is an assistant professor of political science at the University of Zurich, and his research focuses on data science and politics. Lucas is also the co-founder of a company called Leemann, which does online polling in Switzerland and provides prediction of Swiss referendum votes to the newsgroup Tamedia. So Lucas, whenever you're ready, the floor is yours.
Thank you very much. Thank you also for inviting me today to talk a little bit about my work, and especially thank you very much for organizing such an event in these times, which didn't make it easier. So as you mentioned, I have kind of two different hats. On the one hand, I'm an academic working on various issues that fall into data science and political science, or the intersection thereof. And on the other hand, I'm the co-founder of Leemann. And so what we do in that is essentially a data science company working specifically on political questions. And we are interested in questions that are broadly related to the res publica, so where there is a general public interest. Now, today I want to talk about how machine learning can improve work we do in survey research. So I'm not going to talk about some of our other projects where we leverage machine learning maybe for the projection of votes on a Sunday or so. Today I'm really looking more about what we can in general do with machine learning when it is applied to survey research. And so to start out, I'm going to come with a fairly general problem. And there's different ways of framing that from an academic point of view, but also from a consumer point or a political point of view. So we have a lot of survey data on many items, and these are survey data that are usually generated on some kind of national level and provide us a good, usually, estimate for that average value across the country. But very often the interest is not necessarily in that one number that would apply to the share of people, let's say, that are supporting a specific policy or not. But what we really want to have is kind of an idea of how does the support for this policy vary across different subnational units. So a concrete example here could be that you have a US national level poll, so let's say about 1,500 people, and it's about the support for the death penalty. But what we often want to know is actually how does that support vary from one state to the other? And that is definitely something that academics are extremely interested in, but it is also interesting for various other groups. So specifically, when you think about Switzerland and referendum votes or initiative votes that intend to change the constitution, well, there's a double majority requirement. And so that means it's not enough that you just have the majority of votes. You also need the majority of cantons agreeing. And so you might be interested using survey data in advance to kind of get an idea where are those cantons that are going to be somewhat closer to that 50% line to a little bit understand. So these are the places most likely where it's going to be decisive what happens. So to get an idea which ones are the swing cantons, if you want to call them that way. Okay, so a fairly standard problem. It's also known in other fields as small area estimation. So you find yourself with fairly large data and you want to be able to make statements about the smaller units. So up until now, you might say, but wait, why is that a problem? I can just look at my data and I'm going to have people from the various states and I can just use them to come up with that local estimate. That is correct. You can do so, and you're going to do fairly well in the US, for example, for California, because it's a large state and it's going to provide you with a lot of respondents. And so it's going to be fine to use that. But you're also going to have states like Wyoming or Delaware, and that's not going to be that easy because you're going to find very few people. Flipped back to Switzerland, if you have Swiss data, you're going to do fairly fine for the Canton of Vaud or the Canton of Zurich. You're not going to do very well for Jura or for Appenzell-Innerrhoden. So it is these medium and smaller sized places that are causing an issue. But okay, as mentioned, this is a problem that has been around for some time, and there's also a fairly, by now, I would say, standard solution that academics use for it, and also applied research. So companies like YouGov or so, if you think about YouGov's operations in the UK, a lot of their modeling is based on MRP. So MRP is multi-level regression with post-stratification, and it's a way to overcome the issue we have with fairly noisy local estimates. And the idea is that you first have a modeling step and then you have a post-stratification step. So if you know how post-stratification works, then you remember that the core of it is for these subgroups to have that mean estimate. That's just like the data mean you have. And here what we're going to do is we're going to replace that with a modeled response. And that is what helps us to like overcome these issues with these local estimates. So to just give you a very brief flavor, rough idea of what this actually does is you can write it down as a thing like this. This is like a very simplified example. But what is important is that essentially we have some form of like binary story here. So we're assuming that there's opposition and support for a specific policy item that you want to know. And then what you're going to do is you're going to model it as a function of various responses. So you see these alpha J's, alpha K, alpha M, that stuff that we have there to the right. Those are the random effects. And that is where the individual level information from the survey comes in. So that could be gender, education, age groups, income groups, and so on and so forth. So that is the stuff that we put in via random effects. So that is already exposed to a certain regularization. So it's a little bit shrunk towards zero. The one thing I want to point your attention to is there's also this beta 1 X rep here. So you could imagine that if you want to understand what is the state level support for the death penalty in the US, then there's not only individual level factors that you want to include, there's also context level factors that you want to include. For example, the share of the Republican presidential vote share in that state. And that's going to actually help you get better state level estimates if you have something like a strong predictor on the state level. Apologies. Now, there has been a number of examples recently showing that MRP remains still the standard response to this data challenge, but is not something that just automatically is going to work. And it's kind of like this miracle wand that you can swing and then the good results pop out, but that it's subject like any other method to the various constraints. And specifically here, two people, Budis and Heighton, had done some work to show actually that we need to be maybe a little bit more careful working with multi-level regression and post-stratification than expected up until to that point. Now, what I want to do here and what I've been working on with my two co-authors, Philip Roniecki and Rito Wüst, both postdocs currently in Norway, is think about how can we come up with an improved MRP model. And so what we're really looking here for is a way to actually come up with a model that is capable of estimating these subnational preferences, but kind of outperforms the standard we have. And so I'm going to frame it over feature selection now, but of course it also applies to functional form. Essentially, the problem you face when you look at these models is that on the individual level, you have already included a lot of regularization because you're using random effects to bring in that information. But on the context level, the state level, that's where in the example we have the Republican vote share. On that level, you essentially have nothing built in to protect you from overfitting. Yeah, so it's one of these classic situations where if we just go and start throwing in information and naively looking maybe at our first step model and being like, oh yeah, it seems to be improving. That looks good. Then we're just going to be terribly overfitting on our training data. Now, why this is really unfortunate is because equally we know that these MRP estimates on the subnational level, they mostly improve when you have an optimal set of context level predictors. So that's something else that the literature shows. So it's less about the individual level variation and structure that you have. It's more about picking the right context level factors. So that really means we're a little bit in trouble because we have a method that really seems to be performing well when you get a good set of context level predictors. And at the same time, we actually don't really know how to pick them. So taking a quick look at the existing literature and asking ourselves, well, how do other people do that, or what is maybe state of the art? Then you will quickly realize there's actually no real discussion about a systematic selection. There's one paper I'm aware of so far that in the appendix, I think, has some quick check on AIC and BIC for various model specifications. If you look at these names, which are people that have done a tremendous amount of work on MRP, then you will again see that there's actually no really systematic selection. And so that means it's not so clear how we're going to go about it. Are we just going to handpick these factors because we think they seem to somehow correlate with the outcome of interest? It's also not clear that that's actually a promising strategy. Do you maximize model fit? So there's a bunch of things you can do. And this is where Reto, Philip, and I say, well, look, essentially, this is just a standard prediction problem. Yeah, we have the survey data, and what we want to have is as good as possible context level predictions of support for specific policy items. And we do have a lot of tools available. That's what we want to bring to bear on this issue. So what we're going to do is we're going to try and look for such an optimal or better model by using 5 classifiers. We're going to use k-fold cross-validation for all the classifiers. Then we're going to have an additional fold we're keeping aside because in the last step, we're going to do some averaging over that. So what we have is we have a standard hierarchical model where it's essentially just best subset that we're running, looking at the best combination of factors. Then there's a lasso model that brings in some regularization. Then there's a multi-level with principal components. So the idea that we're kind of trying to shrink the feature space by taking out like the most relevant variation that we find in the data. We also have gradient boosting, and then we have a support vector machine. So we're going to have these 5 classifiers that are going to help us like go and work on this best model. But then, of course, the question is, you get these 5, do you just want to run them and then try and like figure out which one is the best one? Well, ex ante, you might not know that, and our best bet essentially is to use some form of a super learner to combine these like 5 streams of information. We're getting these predictions into one, and that we're going to do with an ensemble Bayesian model averaging EBMA model. So we have this additional fold that we keep on that. We're going to see the relative performance that's going to affect the weights of each of these classifiers. Okay, so this thing we're calling auto MRP because there's an automatic part of the modeling happening here. We have 5 simple classifiers. What is important for you to know is that there's nothing that will like hinder you to use additional classifiers. Also, the way we set up the software is such that you can add additional classifiers if you want, or you can drop some of the existing ones. So it's a very flexible setup, and it allows to systematically come up with more optimal models. Now, you might be interested in how this thing works or how it compares. So what you see here, and really just briefly, there's essentially a reference data set that goes back to Budis and Huyton. It's 89 items where you have at least 25,000 observations. You kind of select a small sample, you run your models, and you compare it to the pseudo population there. And what you get here is this baseline, the third bar from the left. That is the standard specification that you would find there. And you see when we apply EBMA, then we actually get about a decrease of 12% points in the mean squared error. Another thing that comes up is the uncertainty. So part of this can also generate uncertainty. The problem is because you're going through these many steps and there's not like analytical or easy expressions of this uncertainty from the individual steps, we end up doing essentially some form of bootstrapping. So it's very computationally extensive to come up with uncertainty estimates, but it's possible. Last point is that you might think, well, they're probably not the only ones who have that idea, and that's absolutely right. So there's a bunch of other people who have thought about how can we leverage insights or tools from machine learning for exactly this problem. And so there's BARP, Bayesian additive regression trees combined with MRP. There's SRP, stacked regression and post-stratification. Then there's auto MRP. We go back to the standard like benchmark data sets, run all of them. And what you get here is fairly encouraging results for the auto MRP compared to the other two available options. Okay, so this is a disciplined approach that outperforms the baseline most of the time, but that's 70%. That means in 30% of the instances or items you would have maybe done better using the baseline. You get uncertainty. If you want to do it yourself, the R package is on CRAN. You can download it. It's auto MRP. And as said, so far, it seems that it is outperforming the two alternatives that are existing. Look forward to your questions.
Thank you, Lucas, for the nice presentation. We don't have a question from the audience yet, so please don't be shy and ask some questions. But I have a question for you. So your approach seems to work very well on a held-out data set in Insights. Can you maybe elaborate a little bit on predictions and the performance that your approach has achieved on real data? After you've trained your model and then you're making predictions for the next vote, let's say on March 7, how accurate is your approach?
Thank you for the question. So I think I wasn't clear enough. So the way we evaluate this model here is by using the data from Buddes and Heiten. And what that is a huge collection of survey items across various surveys, creating something like a superpopulation. So you get a survey item and you find yourself with sometimes up to 35 or 40,000 people that responded to that very item. And what we do here is we kind of draw a sample of 1,500, and then we pretend that that is the sample we have and that the true population is the 40,000 or so people that responded to it. And that's how we run the benchmark, because then it is a random sample from that group. That's how a lot of this work in MRP is doing. Now, if you want to see how some of these things work, then it would be interesting to go and look at the subnational level. So we had, for the last vote, for example, a simulation showing you that essentially if we're not around 53, 54% yes vote in the popular vote, we do not even have to go and look at the majority of cantons. And that's, of course, then what we saw in the sense of we had a support that was lower, so barely above 50% or 51, but it didn't suffice. Like, it wasn't necessary to go and look at the majority of cantons because the support was so low. And so in the background of that, and coming up with this number where it starts to matter, is, of course, a model that was looking at the support on a canton level.
Okay, thank you. That was very clear. And there is one question from the audience. The question is by Gabrielle Ras, and she's asking whether deep learning models are ever used on this type of problems, and especially because the data sets are rather small. So can deep learning models be used on these kind of problems?
So there's two questions. Does anybody do it, and could it be? So as far as I'm aware, nobody is doing that. And I think part of it is exactly what is mentioned. Like, it's not a huge data set at the end of the day, especially if you think about how some of these tools are otherwise used. When you compare that, then it's more like a small data problem, not just a small area problem. I am not aware of anybody applying it on this kind of like feature selection, or in general, like on this like first level survey data analysis. I'm also not sure if that's really what you need here. I think at the end of the day, we have to be a little bit humble and accept that we're working with survey data. And survey data comes with a lot of built-in error components. And so at some point when your process is so noisy, it's not clear if your best approach is to get an even more a sophisticated tool, or whether you would not want to spend that somewhere on trying to like do something on data cleaning or something like that.
All right, thank you very much, Lucas, for the presentation and your answers.